In the far reaches of our solar system, where sunlight fades into a pale, cold glow, drifts an ice giant of haunting beauty, Uranus. A planet that tilts on its side, spinning like a rolling sphere through the dark, cloaked in pale blue clouds and secrets still unspoken. For centuries, Uranus remained an enigma. Its faint glow made it nearly invisible to the naked eye, a ghostly wanderer on the edge of perception. When William Herschel first spotted it in 1781, the world expanded, literally, as humanity realized the solar system was larger than once believed. Yet even today, Uranus remains a puzzle. We've only visited it once, a fleeting encounter by Voyager 2 in 1986. The data we captured then was just a whisper, a single glance at a distant, frozen world. But among the mysteries that Voyager uncovered was something astonishing, a massive, swirling shadow on Uranus's surface, the Great Dark Spot. Like the famed Great Red Spot on Jupiter, this was no ordinary blemish. It was a storm, a vast, spinning vortex, large enough to swallow Earth, yet unlike anything we had ever seen before. Then, as mysteriously as it appeared, it vanished. Later telescopic observations showed no trace of it, as though it had dissolved into the ether. But in recent years, new observations from the Hubble Space Telescope have reignited the mystery. A new dark spot appeared on Uranus, eerily similar to the one Voyager captured decades earlier. What are these shadowy storms? What forces sculpt such massive vortices in the ice-cold atmosphere of Uranus? And could they hold the key to understanding how planets, even those at the edge of sunlight, remain alive, dynamic, and evolving? To unravel Uranus's Great Dark Spot mystery is to peer into the hidden mechanisms of an alien world, a world that may not be as quiet as it appears. Uranus may look calm from afar, but beneath its soft blue hue lies a world of extremes. Composed primarily of hydrogen, helium, and methane, it is classified as an ice giant, a category distinct from the gas giants Jupiter and Saturn. Here, volatile ices like water, ammonia, and methane mix deep below the clouds, forming a mantle that is both fluid and alien. Methane gas high in Uranus's atmosphere absorbs red light, reflecting shades of blue and turquoise, the very hues that give the planet its serene appearance. Yet beneath that calm exterior lies a cauldron of atmospheric dynamics. The winds on Uranus can reach speeds of over 500 miles per hour, whipping across a planet colder than any other, with temperatures dipping near minus 370 degrees Fahrenheit. And then there's its tilt. Uranus's axis is inclined by an astonishing 98 degrees. It essentially rolls around the sun on its side. This means that for decades at a time, one pole basks in continuous sunlight while the other lies in unending darkness. Such bizarre lighting conditions drive extreme seasonal variations, likely influencing the formation and behavior of the planet's mysterious dark spots. Deep within, Uranus's structure defies expectation. Unlike Jupiter and Saturn, Uranus emits almost no excess heat. Its internal energy, the residual warmth from its formation, seems muted, as though the planet's core were cooling differently from its peers. Yet somehow, immense storms still arise in its upper atmosphere. What could power such tempests in a world that should be still and cold? Is there hidden heat buried deep within Uranus's interior, a secret reservoir of energy trapped beneath layers of ice and gas? Or do these storms draw their strength from sunlight alone, magnified through complex chemical and thermal processes we are only beginning to understand? The Great Dark Spot stands as the most striking clue, a visible manifestation of invisible forces, a shadow revealing the hidden life of a planet that appears frozen in silence. When Voyager 2 approached Uranus in January 1986, humanity saw the planet in detail for the first time. The spacecraft's cameras scanned its icy blue face, revealing a strangely featureless sphere. Unlike Jupiter's tumultuous bands or Saturn's swirling storms, Uranus seemed calm, almost eerily still. But beneath this quiet facade, subtle variations hinted at deeper activity. Decades later, when the Hubble Space Telescope turned its gaze toward Uranus, something remarkable emerged. A vast, oval-shaped feature, dark and brooding, swirling high in the planet's northern hemisphere. It was the Great Dark Spot reborn, echoing the storm seen decades earlier by Voyager. These spots are not fixed landmarks like Jupiter's red spot. They appear and disappear over the course of years, ephemeral and elusive. Each dark spot is likely a window into Uranus's deep atmosphere, a massive, high-pressure vortex formed by turbulent motions below the visible clouds. Within these storms, methane ice crystals and other aerosols form bright companion clouds, glowing against the dark void. What makes Uranus's dark spots so mysterious is their fleeting nature. They seem to materialize suddenly, grow to planetary scales, and then dissipate, as though the planet itself breathes, exhaling and inhaling its storms in rhythm with unseen cycles. Recent observations from Hubble and other telescopes have shown that these storms may be tied to Uranus's changing seasons. As the planet's poles shift in and out of sunlight over its 84-year orbit, thermal imbalances could ignite massive atmospheric disturbances, storms that churn up dark material from deep below the cloud tops, creating the eerie spots we see. In 2019, NASA's researchers identified another new dark vortex, the latest in a lineage of storms that seem to mark Uranus's slow, mysterious pulse. Each one adds to the enigma. Why do they form in certain regions? Why do they fade? And why does Uranus, unlike Neptune, produce such transitory, unpredictable tempests? To answer these questions, we must look beyond observation and into simulation. We must recreate Uranus in the digital realm. On Earth, scientists can model hurricanes, predict weather, and understand how energy moves through our atmosphere. But to model Uranus is to enter a completely different world, a realm where chemistry, temperature, and physics behave in alien ways. In laboratories and supercomputers across the world, planetary scientists are using advanced simulations to recreate Uranus's atmosphere, from the turbulent winds of its upper layers to the dense, supercritical fluids deep below. Artificial intelligence now plays a vital role in this research, helping scientists process vast amounts of data from Hubble, Keck, and the James Webb Space Telescope. By training machine learning models on planetary weather systems, AI can identify recurring patterns and anomalies in Uranus's storms. It can simulate how methane condensation, sunlight scattering, and thermal convection interact to form massive vortices. These digital models reveal that Uranus's great dark spots may originate deep within, born from powerful upwellings of heat that break through layers of methane haze before dispersing. Yet, despite their alien nature, these storms share something familiar. They remind us of our own planet's dynamic weather systems, of cyclones, hurricanes, and jet streams that dance to the tune of physics and sunlight. Through simulation, we begin to see Uranus not as a static world, but as a living system, one that changes, evolves, and expresses its energy in unpredictable ways. These digital windows into Uranus's atmosphere bring us closer to understanding not just this strange planet, but the behavior of ice giants across the galaxy. And that understanding carries greater implications, for Uranus is not just an isolated mystery. It is a prototype. Billions of exoplanets may share its composition and dynamics. By solving the riddle of Uranus's great dark spot, we may unlock the secrets of countless worlds beyond our solar system. Uranus, the quiet wanderer of the outer solar system, is far more alive than we ever imagined. Beneath its tranquil surface, unseen storms rise and fade, sculpting the planet's hidden rhythms. The great dark spot, ephemeral, powerful, and mysterious, is more than a weather pattern. It is a message from a distant world, reminding us that even in the deepest cold, energy and change persist. In its stillness, Uranus whispers the story of balance between light and darkness, between silence and motion. Its great storms, appearing and vanishing over decades, teach us that even in the most remote corners of the cosmos, the laws of nature remain universal.